Hi class, so this next video is on singular value decomposition. This is another method of breaking down our matrices and factoring them into pieces. This is again another very important type of factorization. It is used very often, again very often in quantum mechanics, but also used in things like finance, pretty much everywhere, you guys. All this stuff is super important. I can maybe click some links for applications of these things later. I feel like the videos are really meant to just talk about how to do the methods, right? So let's get started. Okay, so here we are going to talk about how to factor things into three parts when they are again not square. This is different from the QR factorization because here we are basically going to make a symmetric matrix and then diagonalize it the way that we were doing before, or orthogonally. Okay, so really what we want here is we would like to have more rows than columns. Okay, so we want the number of rows to be more than columns. We will talk about what to do if this is not the case. If we have more columns than rows, it's actually a pretty easy fix. Again, let's say that they were even, it was square. If it was square, then we would do our orthogonal decomposition, right? So orthogonal diagonalization is when everything is nice, things are square, yada yada yada. So how do we decompose things basically that are not square, because we're not always going to have a square matrix, right? So that's really what we're talking about today, is how do we diagonalize things that are not square. Okay, so what we are going to do then is we have a whole process. Okay, so the singular value decomposition, or SVD for short, okay, is a factorization of A where we have again three parts. We have U, we have sigma, and we have V transpose. Okay, so let's talk about each of these things one at a time. Okay, U is going to be an orthogonal n by n matrix. So again, an orthogonal matrix does not mean just that the column vectors are an orthogonal set, right? It is also normalized. So each column vector is orthogonal to the others. They form a right angle, dot product of 0, and each vector is normalized. Okay, so don't forget the normalization part. I feel like that's the most common thing that people will leave out because the name orthogonal, just implies that it's only orthogonal, but it is also normalized. Our sigma matrix, this is going to be our diagonal matrix. So remember, for P inverse or P transpose for the orthogonality, this middle matrix was our diagonal matrix that had our eigenvalues on it, right? Here, our matrix is n by m. We can't find eigenvalues for something that's not square. We are going to be finding eigenvalues, right? But what's going to happen is that this is not typically going to be a square matrix, right? It's going to be n by m. More rows than columns. It's going to have the same dimensions as A. So we're going to make it as diagonal as possible, okay? Which means we're going to have a row of zeros in there most likely, but we will still have entries along the main diagonal. We'll just have some fluff zeros sort of at the bottom, okay? So the way that this is going to look is that we're going to have a matrix of zeros on the bottom and our diagonal matrix on top, okay? So D is our square diagonal matrix, and then we're filling the rest up with zeros. So it's as close to a diagonal matrix as I can get for n by m. Okay, so the first square portion of it, right, for as long as many columns is the same size as the rows, that will be a diagonal matrix. The rest are just rows of zeros. Okay, so the diagonal matrix is here. Here, these sigma values are called our singular values. Okay. So sigma I are the singular values. So again, this is large sigma. The entries are little sigma, right? So again, Greek letters. Capital sigma is the capital, right? This is the lowercase of a sigma. If you ever took in what do you call it, probability or statistics, and you've seen these values before this this symbol. They are not the same thing as in statistics. Okay, so don't mix that up. It's just the same symbol, but that's what this is. So this is the uppercase sigma, and these are the lowercase sigmas. So each of my sigmas, each of my singular values are positive or zero. They can be zero, but they're going to be positive. Okay, there should be no negative values inside of this large sigma matrix. Okay, so the sigmas are the square root of my eigenvalues that I'm going to find here. Okay, right? That's why they can't be negative, because they're square roots. Otherwise, they'd be imaginary, right? So the sigma i's, these are going to be the eigenvalues of A transpose A. So if you remember from the previous video, A transpose A will give us a symmetric matrix, and the eigenvalues from this symmetric matrix, they will always be positive, right? That was one of the theorems that we had for the A transpose A eigenvalue values, right? It was one of the theorems. Okay, and here you go, right? Recall that these are always positive or zero for A transpose A. Okay, so that's the U, right? An orthogonal n by n, obviously that's going to come from the eigenvectors that I'm going to find from this A transpose A, right? Because it's orthogonal. And this V transpose is going to be an orthogonal n by n matrix also. Okay. Let me just make sure I didn't get that confused. Yes, U is going to come from the eigenvectors of these lambdas. Okay. So what if we have more columns than we do rows, right? So what if I have a long ways, it's longer this way than it is this way, right? So what we're talking about right now works for when my my rows are longer than my columns, right? So what if it's the other way? If it's the other way, that I have more columns than I do rows, well, it's actually pretty easy. We just transpose A, and then the transpose of A will bring us back to this world, okay? But we have to adjust our formula a little bit, right? So I transpose my matrix so that I then am in this case, right? So if my columns are more than my rows here, the transpose will make me have more columns because I'm flipping it across the main diagonal. But that's going to change my formula, right? So before, my formula was U sigma VT. Sorry, you guys, this should just say A transpose. So this is not equal right now. I'll fix that in the write-up. Okay. Okay, what it should say is that if I take A and take the transpose of it, then I'm taking the transpose of this, right? And so this is what I'm going to get. Oh, I'm sorry. No, I did write this right. Let's back this up. Okay. If I take the transpose of A, I am then in this world, right? And so my SVD decomposition of my transpose will have this same formula. It'll be a U sigma VT, right? So remember, A here is now, A transpose is in this case because the original A had more columns. So when I transpose it, it'll look like this. So what I do is I transpose it. I do all of my original stuff that I'm going to show you how to do. I find the U, I find the sigma, I find the V transpose, okay? So the A transpose looks like something in here, and so this is its decomposition. But I got to bring it back to the regular world of A. I got to bring it back, so I'm going to just transpose both things. So I'll transpose A to bring it back to this A where I have more columns. And so I transpose my results also, and this is what it will look like. Okay, it's the same V, but I'll transpose my results. That sigma that I have, I'll transpose that, and that U that I would have had from here, I transpose that and I multiply them in an opposite order. So if you're like, what the hell are you talking about, Professor Williams? Don't worry. I'm going to do one of these, and then I'm going to show you how I would have changed it or how it would be different if my matrix started out differently. So we'll show this as in an example. The most important thing is to understand how to do this, right? Because if we can do this, then we can do this part and then just adjust it at the end. Okay, that's really the way that we work the more columns than rows, is we just work it like this and we change things. Okay, so let's talk about this. That means that every matrix that is not square will have a singular value decomposition. So now again, we're basically learning how to decompose any sort of matrix into some sort of diagonalization. Okay, if it's symmetric, we can orthogonally diagonalize it. If it's not symmetric but it's square, we know how to diagonalize it. Okay, we've talked about that in chapter 6, I think it was, or 7, right? A couple weeks ago. If it is not square at all, then now by SVD we have a method of diagonalizing it. Okay. So, and then we have one more factorization, which we just got done talking about last video, which is the QR factorization, but that is not a diagonalization. Okay. So, process. Okay. So for when we have more rows than columns, okay, our standard model for this, again, when we're not in the standard form of this, then we just put it into the standard form by transposing, do all the stuff we're going to do now, and then adjust our results by this formula. Okay. So first thing we want to do is we're going to orthogonally diagonalize A transpose A. Okay, so we're going to turn it into P, B, P inverse. So we're going to use the methods that we learned in the last video. So we used in the last video, I call this the PD, like David, PD, P inverse. But we don't want to call D, we don't want to use D here because D is used inside of our sigma. So I'm not using D, but this B, like B's matrix, that's just our diagonal matrix. Okay, so we're going to take A transpose A and we're going to diagonalize it. I'm not calling it D because the D that will be here is not the same as the D that's going to be here. So we're not going to use the same name for two different things. So we're just calling it a different name, but it's still the PDP inverse method, right? P, like Philip, like my name here, this is going to be orthogonal, right? So P inverse is just the transpose of P, right? If you're still fuzzy on that, refer to the previous video that we did. That's where we talked about orthogonal diagonalization, right? Remember, this is going to be symmetric. When we diagonalize it, we have certain properties that pop out, okay? So we're going to orthogonally diagonalize this into the PB, P inverse. We're going to find V by normalizing that P. Okay, it's that P matrix, that's going to be my V. And then I'm just, but I have to make sure it's in the proper order. Okay, so before when we did this, I could have thrown it basically in any order as long as the eigenvectors in the P and the eigenvalues in that diagonal matrix matched up. Here, that's not the case. I have to put them from largest order to smallest order because these have to go from largest to smallest also. Okay, so the eigenvectors that are in V, in my P matrix, they need to be normalized, obviously, right? Because it's orthogonal. But it also needs to be in descending order. The largest eigenvalue vectors are first, okay? And then go to the smallest eigenvectors that are associated with the eigenvalues. 3 is I find my singular values. It's just going to be the square root of each of my eigenvalues for this symmetric matrix, this A transpose A that I made. And then I'm going to put those diagonal entries into that sigma, that as diagonal as possible matrix that I have, in order from large to small, the same order that I have their eigenvectors. Okay, so again, they got to match up, and they're matching up from largest eigenvalue down to smallest eigenvalue. Okay, 4 is a little bit wordy, but let's kind of read through this. Okay, so as long as I am inside of a row, that is less than the square matrix, right? So as long as I'm still building this sigma, okay, then each column of my U vector is going to have this form. 1 over that singular value times my original matrix A times the ith vector of V. I know this looks confusing. There's a lot going on here, but once you do a few of these, it's not as bad as it seems. Okay. Now the remaining vectors of U, okay, because remember, I have more rows than I do columns, so I'm going to end up having to kind of fill in some entries here, and we're going to do that by using a basis for the column space of the orthogonal complement of the column space of A. Okay, so an orthonormal. So we're going to find this basis, and we are going to normalize it. Okay, it'll be orthogonal by default. Okay, but we will have to normalize the vectors that form this basis. So you might say, what the hell is the orthogonal complement of the column space of A? It's just the null space of A transpose. Okay, that's going to be the easiest way to think of that. We're going to transpose A, set it equal to 0, solve for it. We'll have some free variables. Those vectors that pop out are going to be the basis. We've done this before. That's not super crazy. We've done column space too, but column space of an orthogonal complement is somewhat strange. So we're going to relate orthogonal complements to our transposes, and we're going to have to look at the properties of A transpose A, because certain things have to hold true for A and A transpose A, right? So let's look at these. So these things are going to form the remaining columns of U. So those remaining columns of U, those remaining column vectors, will be formed by this basis for the null space of the A transpose. So here's the theorem. This theorem is going to relate the properties of A to A transpose A. So if A is n by m, okay, here we're not saying that more rows than columns or which one is larger. We're just saying that this is an n by n matrix in general. We have that the null of A is equal to the null of A transpose A, right? The row of A, the base, so remember this is a space, okay? The row space of A is equal to the row space of A transpose A. The column space of A transpose is equal to the column space of A transpose A. The rank of A is equal to the rank of A transpose A. So remember, the rank is a actual value, it's a dimension. Okay, A transpose A is orthogonally diagonalizable, right? We've already talked about this. This will give me a symmetric matrix. I can diagonalize it orthogonally, and its eigenvalues will all be positive, right? So these two are coming from the last section. Okay, so let's start with an example. Okay, we'll start with a nice example that matches this process where my number of rows is more than my number of columns. Okay, so we're going to find the SDV, the singular value decomposition of this matrix, right? So I have 3 rows, 2 columns. That matches what I have going on. So at the end of this example, what we're going to do is we're going to say, how would we have done this if A was the other way, that it was like 2 rows and 3 columns. Okay, so again, right now we're in the nice process, right? The nice method, the one that we're looking for. Okay, so we want to have more rows than columns, and the short answer again is that if we don't have more rows than columns, then we make it have that by transposing our matrix. Okay, so A transpose A will give me a symmetric matrix. Those eigenvalues will all be positive or 0, and I can orthogonally diagonalize this matrix. That's what we did in the last section in what was it, 8.2, right? 8.3, sorry. So A transpose A, so we multiply first row by first column, second row by first, second column, and so forth. And we should get this matrix, right? Do you recognize this? I said we're going to use this a lot. Okay, so if you haven't noticed, I must have decomposed this at some time, right? So I have 2, 1, 1, 2. So we've already done a lot of work on this already. In fact, I've already diagonalized this matrix in the previous videos. Okay, so that will help us to kind of get through this process. We'll still go through everything like we're doing it for the first time, but you should check that in your notes. You should have this matrix and a lot of its things, its work already. You should already have the diagonalization of this, right? So you should already have the eigenvalues, the eigenvectors, the orthogonal diagonalization of this. Everything should be available for you already if you go back and look in your notes. But let's go through the process again. Anyways, my characteristic polynomial is lambda minus the main diagonal, and then I change the signs on the other diagonal, and then we get a very easy polynomial to solve. We can factor it very easy, and this characteristic polynomial being 0 gives us our eigenvalues, which are all positive, as we said we were going to have. So for my eigenvectors, I can plug this back into my equation here and set it equal to 0. Okay, so last time I did this, I did not set it to 0, so I'm trying to be a little bit nicer because we have a long process ahead of us. So you can see that row 1 and row 2 are identical, so I can make this all positive and make this all go away, and or not. But regardless, I get x1 is negative x2, and so that's my first eigenvector for this symmetric A transpose A that I have, right? Do the same thing for lambda 2. Okay, so I do the same thing. I set it equal to 0. I solve this. If you notice, we have, if I add this to this whole second row will disappear because it's a dependent system. So I have x1 equals x2, which gives me my second eigenvector, which is 1, 1. Okay, so we can form P in order of eigenvalues from largest to smallest. So before I just put x1 and x2 to form my P. Remember, for singular value decomposition, I have to have them in order, meaning since this eigenvector goes with lambda 1 and this eigenvector goes with lambda 2, I have to switch the order because lambda 2 in this case is larger than lambda 1, and that's just because of the order that I decided to do it, right? So in practice, maybe you do it with the largest first and then work your way down. That way you don't have to stop, you know, your flow of mathematics, and you can just go to the first one, second one, third one, what have you, right? But for me right now, I got to go backwards to build my P. Okay, so for me, P is x2, x1, and again, that's because of the order that I found x1 and x2 in, right? So it looks like this. So in the previous video, it was switched around. Remember, the eigenvectors have to go in order with their eigenvalues from largest to smallest. So this is associated with lambda equals 3, and this is with lambda equals 1, right? Smallest to largest. So that would be my P. V is the normalized form of this. So I get this for V. So this is very similar to what I had to before from the previous video, but again, the order is switched. And so that's my V. So for me to find V transpose, right, if you come back here, I need U, sigma, and V transpose, right? So I have V already, so V transpose is going to be easy to find. So now that I have V, let's find my sigma. So my sigma is just the square root of my eigenvalues in order of from largest to smallest. So if you notice, this is, as we said before, as diagonal as possible, right? I have, for the square on top, it's diagonal, and then I fill everything else with zeros row-wise, okay? So this is as diagonal as I can get it, because this has to match dimension-wise with A, right? 3 by 2, 3 by 2, right? So it's as diagonal as I can be. And remember, the values here, these singular values, they're just the square root of the eigenvalues for the same order of these eigenvectors. Okay. Sigma 1 is square root of lambda 2 because I have the eigenvector for lambda 2 here. It's the largest, so that's square root of 3. And the other one was 1, right? So 3 is larger than 1, so there you go. Okay. So now we need u. Okay. So if you remember, the way that I build u has to come from a formula. So the formula is 1 over the singular value times a times the v that's associated with that eigenvalue, right? So for the first one, so here we go. We need 3. 1, 2, 3, because u is going to be square. So let's come back over here again. Okay. U is an orthogonal n by n, right? So it'll be the same size as the rows that you have. So since I'm 3 by 2, my u should be 3 by 3. So I need 3. I'm going to need 3 vectors. Okay. So u1 is going to be 1 over sigma 1, where the first eigenvalue square rooted, right, or singular value, times my original matrix A times that normalized vector, that normalized eigenvector that's associated with that singular value. Okay. U2 will be the same, right? Notice I only have 2 eigenvectors, right, from V1 and V2, so U3 will have to be formed by looking at the null space of A transpose. Okay, I have to look at null space of A transpose because I've ran out of vectors in order to use this formula with. Okay, so let's just plug this in. I'm going to have 1 over square root of 3 times A times this V1. Okay, 1 over my singular value, my first one, times my A matrix, times the column vector, that normalized column vector, that normalized eigenvector that's associated with the singular value. Okay. So then I have a 3 by 1 vector here. My U2 will be the same thing. It'll be 1 over 1 times A times this normalized eigenvector also. Okay. So 1 over 1 is just 1 times this column vector here, the normalized eigenvector for that singular value. And this is what I'm going to have. So now I have the first 2 columns of my matrix U, right? Those are pretty easy to find. Just make sure you refer to the formula. So the last thing that I need is U3. Okay, so I need to find the null space, the basis for the null space of A transpose. So what I'm going to do is I'm going to take A, I'm going to transpose it, right? So I'll put it on its side. I'll set it equal to 0, and I'll solve it. So notice if I put this on its side, I'm going to have 2 rows with 3 columns. So when I reduce that to my echelon form, I will have 1 free variable, at least, right? And so from that free variable, I can build a vector, and that vector will be my U3. Okay. So the column space of the orthogonal complement of A is going to be the null space of A transpose. So I really just need to find the null space of A transpose. So I'm going to transpose A, set it equal to 0. Very easy to reduce down, right? It's really just 1 row operation. I don't even have to put this in my calculator, honestly. Okay, so I'm going to have a free variable at x3, okay, or u3, whatever you want to call it. So that's going to tell me that x2 is x3 and x1 is negative x3. So that's going to give me a vector. All right, if I let x3 be 1, x2 is 1, and x1 will be negative 1. So that is going to be my u3 vector. Okay. If there were more basis vectors, then we would need to use them to build an orthogonal set through the Gram-Schmidt process, if they were not orthogonal already. Okay, so what do I mean by that? Let's say I had two free variables. Okay, if my two free variables gave me a basis that was not orthogonal, I would have to make them orthogonal through Gram-Schmidt if they were not orthogonal already. Okay, U must be orthonormal. It has to be orthonormal. So I need to normalize this, and that is also why I would need to build an orthogonal set through Gram-Schmidt if the two free variables did not give me two orthogonal vectors. Okay, so since there's only one vector, I don't have to worry about Gram-Schmidt. I just have to normalize the one that I have. Okay, so I'm going to divide this by its own length, and that will give me my U3, right? Because this is not normalized. So this is my U3 vector, and I can throw all three of those together now to form that U matrix, right? So that's U1, U2, and U3. So U1 comes from the first singular value and the first normalized eigenvector. This comes from the second singular value and the associated normalized eigenvector, and this comes from the normalized vector that gives you a basis for the null space of A transpose. Okay, that's where these three things come from. So now I have everything, right? We'll go back. I have a V, I have a sigma, I just found U. So I need to go ahead, we'll come all the way back real fast, and I need to throw them all together in this form. U, sigma, V transpose. Okay, now that I have all the pieces, I can put them together. There we go. Okay, and I got U, sigma, V transpose. Okay, so I transpose the V. The sigma is as diagonal as possible. This is the same U that I just built. Okay, and again, I have to check, right? Multiply these things together. Okay, if you multiply them together, you should get this matrix, which is A. Now again, if you have something missing, you did something wrong. So for instance, if you multiplied all these out and then here you get something like 99 over 100, right? Almost 1. You can't say, oh, I was close enough. I got pretty much everything right. No, it should come out exactly. There's something wrong somewhere, right? So you got to go back and figure it out, okay? Now let's say that our example was this form of A, okay? So this is A, but let's say that as I said before, I had more columns than I do rows, okay? Well, what I would do is I transpose A to give me this. I can call it a new name, B, if I want, right? So I would transpose it so it looks like this. I would do my whole process all over again, okay? Everything we just did, I would do. The only difference is that the first thing I do is transpose first, so that I have more rows than columns. So once I'm done and I find all of my stuff, because again, if I did the work I just did before, I'm going to get the same U, sigma, and V transpose. I'm going to get all the same things here, okay? So the only difference then is I don't transpose V, and I put it in front. This sigma, I would transpose it, and this U, I would transpose that, so it looks like this, okay? So I switch the order around, and I'm going to transpose basically everything, right? So now it's going to look like this, and when I multiply it out, you should check this, I will get my new original A, okay? So again, if I have more columns than I do rows, transpose it, do all the work that we did before, but I just put my results in a different order than I normally would, okay? Because I got to come back to this sort of rotated form of my matrix, right? And that is our singular value decomposition.